So first, thanks to the...
Yeah, we'll find out. Okay.
Thanks to the organizers for having me. This has been a very educational conference so far, and I'm excited to tell you guys about this project called First Price Auctions with General Information Structures, and it's joint work with two individuals who should be well known to this audience. So before diving in, I just wanted to frame the exercise. I think it's kind of useful to talk about how this work fits in with the shared perspective that this CS and econ crowd have. So this paper is going to be about first price auctions, and the classical methodology for thinking about first price auctions that say comes from Vickrey would be to say, let's fix a distribution of values. Vickrey started with an independent distribution over the bidder's values, and fix an assumption about the knowledge that the bidders have, namely that values are independent and private, the IPV setup, meaning that I know my value, but I don't know anything about others' values except that it's drawn from this independent prior that everyone knows. And one way to view the AGT perspective is to say that this model is not quite right. Once you specified all this, it's great because you can do all sorts of interesting things with it. You can talk about welfare properties of first price auctions. You can compare that mechanism to other mechanisms. But it's not quite right in the sense that when in the real world do we ever know exactly what F is? So when do we ever feel that confident in the assumptions of our model that we're basing these predictions on? And so AGT says, let's think about predictions about welfare outcomes in the first price auction that aren't so sensitive to the assumption of a particular distribution F. Let's vary F and see what happens. Okay? Now the exercise that I'm going to talk about today is in a sense complementary to this perspective. We're also going to take a point of view that the classical model isn't quite right, but not because of the distribution of values, but because of this assumption about information. Okay? And we're going to say, when in the real world are we that confident that the bidders just know their own value and don't know anything about others' values? Or when are we that confident to write down a particular parametric form for what that information should look like? So our exercise is going to be about making predictions about behavior in the auction where we vary information. And of course, you can also think about combining these two exercises and saying, what can we say about behavior in the auction where we're varying distribution of fundamentals and also varying information? And to my knowledge, there are people in this room who are working on that combination, on that combined exercise. But for today, I'm just going to focus on this piece. Okay, so that's my basic preamble and setup. Now let me give you a model. So this is a special case of the general model that we analyze. There are two bidders, and these guys compete in a first price auction for a single unit of a good. These guys have single unit demand. Okay, so it's a very, very simple setup. And they actually have the same value, which is a V that's uniformly distributed between 0 and 1. Okay? And in the auction, these guys submit bids, which are non-negative real numbers. The person who submits the highest bid is going to win and get the good, and they have to pay their bid. So the surplus is V minus B. Okay? So because everyone has the same value and the good is always allocated, efficiency isn't really a concern in this setting. Surplus is always going to be a half, right, which is just the expectation of this value. But the distribution of that surplus between the buyers and the seller is sort of what's at issue and what we'd like to understand better. So the seller's revenue is going to be the expected maximum bid, and then the bidders are going to get the rest. Right? And the broad question is, what are the predictions we can make about how this surplus is going to be split in equilibrium? But at this point, the model isn't completely specified because I've described the distribution of the value, but I haven't said what the bidders know about the value. I have to fill that in. So in particular, what do they know about the value?
Sorry,
yeah?
You said over there something about a half. How did you know that?
I've assumed that the value is uniformly distributed between 0 and 1. So it has an expectation of a half. That's all. And it's a pure common value. Everyone has the same value.
Oh, for surplus, you don't mean there's a price.
The total
Surplus is the value minus the price, or it's just the value?
This is the ex ante value of the good, the total surplus that's going to be generated by the auction for the buyers and the seller. Okay. So I have to say what they know about the value. I also have to say what they know about what others know about the value, etc. Right? I have to specify higher order beliefs. And there are many possible ways to do this. So for example, I could say the bidders don't know anything except for the prior. And in that case, everybody thinks that the good has a value of a half. You're not learning anything about the value from the outcome of the auction. So the unique equilibrium is going to be, Bertrand competition, and the price is going to be exactly a half, and the seller gets all of the surplus as revenue. Here's an extreme opposite. The bidders see everything, and they know that everybody sees everything. In this case, we both know that the value is V, and again, we're going to compete the value up to V. In expectation, the seller is still going to extract all the rents, and the bidders get 0. Okay? But of course, the true information structure we think is likely to be something in between. It's not going to be no information. It's not going to be, but the bidders are going to have some information about the value and some information about what others think about the value. But it's not that easy to introspectively conclude exactly how much information the bidder should have. So here's an example of an intermediate information structure. There are many that I could have given, but here's one. And this is an example from Engelbrecht, Wiggins, Milgram, and Weber. I love that. Bidder 1 is an informed bidder, and he sees the value exactly. Bidder 2 doesn't see anything. Okay? Now, in this situation, bidder 2's strategy has to be independent of the value of the good because he doesn't know anything about it. But bidder 1 can correlate his bid with the value, and that means that in equilibrium, bidder 2 might be learning something about the value from the event that he wins, because he only wins when his bid is bigger than the other guy's bid, right? It turns out that there's an equilibrium in this setting, again, assuming the uniform distribution, where the informed bidder just bids half the value, and the uninformed bidder randomizes between 0 and a half uniformly. So let me quickly try to convince you that this is an equilibrium. Let's first think about the uninformed bidder. So the uninformed bidder is basically facing adverse selection because of the way that the informed bid is correlated with the value. If the uninformed guy bids some B2, then he's going to win whenever the other guy's bid is less than B2, which is when the value is less than twice the bid, because the informed guy is bidding half the value. Okay? Now, what's the expectation of the value drawn from a uniform prior, given that it's less than twice B2? It's exactly B2. So basically, no matter what this uninformed guy bids, his expected value conditional on winning is going to be exactly equal to his bid. So he gets 0, he's indifferent, he's happy to randomize. The informed bidder, on the other hand, thinks that he's facing this uniform distribution. So the surplus that he gets from a bid of B1 is going to be V minus B1 times some linear term in the bid. And, it's not, we're all pretty good at calculus, so it's easy to conclude that the optimal thing in this case is to bid half the value. So this is an equilibrium. And it's also not hard to see that now the bidders are going to get some surplus for themselves, because basically this informed bidder is always shading, and there's a positive probability that he's going to win. So he has to be getting some positive rents. And in particular, he gets a 6th. The takeaway from this example is that the way we model information has a big impact on the outcome of the auction. Okay? And the reason is that your optimal bid depends on not just what you think the value is, but also on what you think others are going to bid. And of course, that depends on what they think the value is and what they think others are going to bid, etc. So the equilibrium depends in a kind of complicated way on everyone's higher order beliefs. And this is as opposed to, say, a second price auction, where, if you make stronger assumptions like everyone at least knows their value, the second price auction doesn't have this dependence on higher order beliefs, because I always have a weakly dominant strategy to bid my value. Not the case in the first price auction. But as we were saying before, a problem is that it's hard to say which is the correct specification for information. It's hard to point to a situation in the real world where we observe beliefs directly, or that they're easy to measure. Okay, so it's hard to test the assumptions that we make. So our exercise is going to be, what are the predictions we can make about welfare that don't depend on how we model information? So here is a brief overview of the results of the paper before I go back to the example. So basically, we study a generalized version of this model. The value doesn't have to be common. There can be an idiosyncratic component to values. And we basically, but although for many of the results we'll assume that distribution is symmetric. And we leave unspecified the information that the bidders have about everybody's values. And what we do is we characterize tight bounds on welfare outcomes. Namely, we say what is the maximum revenue that could obtain, minimum revenue that could obtain, maximum bidder surplus, minimum bidder surplus, as we range over all possible specifications for information and all equilibria, Bayesian equilibria. Yes?
So when you say Bayesian equilibria, Aren't you assuming that the bidders know what the other guys know, or doesn't
Yes.
that implicitly assume that?
Yes. So there is some asymmetry of information assumed between our perspective as a kind of outside researcher and the agents who are involved in the auction. They know what the environment is, and we don't, and we're trying to make predictions about it. So I agree that that's an assumption, and it's worth thinking about. But it's certainly a natural perspective to take, I think, for certain situations. Okay. And I just want to emphasize again that these predictions that we make are for a given and fixed distribution of values. So you could in principle use this exercise to compute bounds over a range of value distributions using as an input the bounds that we obtain conditional on each value distribution, if that's your cup of tea. Okay, and then I would say that this fits into a kind of broader objective. The first price auction is just one mechanism. It turns out that the analysis of that one mechanism is kind of involved. But more broadly, we'd like to replicate this exercise for a range of mechanisms and talk about set-valued predictions for outcomes and have a somewhat more agnostic but safer way of comparing the performance of mechanisms. Okay, and I already talked about complementarity with other perspectives that are represented in the room. Probably the alarm is going to go off in any second, but absolutely. Or you can stretch your legs or smoke them if you got them. There we go. That's not very disruptive at all. I'm going to just keep going. Okay. How low can revenue go in this uniform example? Okay, that's what I want to explore next. It can't go all the way to zero. That's a pretty cheap conclusion. Why? The only way that revenue could be zero is if everyone is bidding zero all the time. But of course, there's got to be some bidder who thinks that they have a positive value sometimes. And if they follow this purported equilibrium, everyone is tying at zero, but you could bid an epsilon and win all the time. Okay? And of course, you'd have an incentive to deviate in that manner. So revenue can't be exactly zero. It also seems likely that it can go below the level in this Engelbrecht, Wiggins, Milgram, Weber example that I gave you before. The reason is that at minimum revenue, there's some sense in which the winning bid distribution is pushed down as low as it can go. Okay, what's the force that's going to be preventing it from going lower? It must be that if it were to go lower, some bidder would have an incentive to deviate to a higher bid. As in the thought experiment about zero revenue, someone would want to deviate to a bid larger than zero. Okay. So, but in the EMW example, the informed bidder actually strictly prefers his equilibrium bid over any other bid, right? He has this concave objective function, v minus b times b, and v over 2 is a unique global optimum. And actually, I could even use that example to construct other examples that are symmetric in which everyone has a strict incentive to follow their equilibrium strategy. So it's kind of not passing our suspicion that lots of upward incentive constraints should be binding at minimum revenue. Let me give you another construction. Okay. In this specification for information, the bidders are going to get signals, and these signals are going to be numbers between 0 and 1. One of the bidders is going to get a precise signal that's exactly equal to the true value. The other bidder is going to get a noisy signal which is distributed below the true value according to this particular cumulative distribution function, square root of the signal over the value. Okay. So, and one of these guys is going to get a precise signal, one's going to get a noisy signal. They don't know who is who. We're going to randomize, and they're going to be equally likely. And of course, there's the same support for signals, so you can't tell from which signal you got whether or not it was a precise or a noisy signal exactly. My claim is that there's an equilibrium in this setting, which is to bid your signal over 3. Bid 1/3 your signal. So before I attempt to convince you that this is in fact the equilibrium, let me explore some consequences of it. The guy who wins, according to this monotonic strategy, is going to be the bidder who got the higher signal. And the bidder who got the higher signal is always the guy who got the precise signal. So that means that in equilibrium, the winning bid is always going to be 1/3 of the value. And since the value is uniformly distributed, revenue is going to be a sixth. It's a symmetric equilibrium and information structure. The bidders are going to get 1/6 surplus each.
Do they know whether they got the precise or the noisy?
They don't. They just know their signal, but it could have come from either the precise signal or the noisy signal. And they're equally likely ex ante. Okay. Let me try to convince you that this is an equilibrium. Yes? I don't know, but I know that it's the worst equilibrium in terms of revenue. And since my objective is to minimize revenue, I'm looking for the minimum revenue that's sufficient for my purposes. But I don't know if it's unique. Okay. Let me try to convince you that this is an equilibrium. For every signal, we can think about deviating up or deviating down. Let's think about deviating down first. You got the signal S. If it was noisy, you know that the other guy must have gotten a higher signal. So if you follow your equilibrium strategy, you're getting 0 surplus in that event. And if you deviate down, you're still going to lose, and you're still going to get 0 surplus. So we kind of don't care about what happens if you deviate down and the signal was noisy. On the other hand, if you got the precise signal, then the other guy's signal was lower. Okay? And you're still going to win with some positive probability if you deviate down, and we have to do the calculus to determine whether or not you'd want to. So this is actually the surplus that you'd get. You're going to deviate down to a bid S prime over 3. Your surplus will be S minus S prime over 3, because remember, you got the precise signal, so this is the true value of the good. And the other guy's signal is distributed according to this distribution, S prime over S square rooted. Okay? Now, you can hopefully follow Ben's prescription yesterday and trust now, verify later, that I've done the calculus correctly, and the derivative of this expression is positive as long as S prime is less than S, which corresponds to a downward deviation. Okay, so no one wants to deviate down. Let's think about the other side. Now, if you deviate up to a higher bid, we can decompose your surplus into two pieces. Again, there's the event that you got the precise signal, in which case you were going to win by following the equilibrium strategy. You're still going to win with the higher bid. But you're now going to have to pay more, because this S prime over 3 is higher than your equilibrium bid of S over 3. On the other hand, you might have gotten the noisy signal, and now you're going to win on some events where you would have lost in equilibrium. And intuitively, there are a bunch of values now for which you might win, which is when the winning bid would be above S over 3, but below S prime over 3. Okay? And you're going to weight those events by the relative likelihood of you having received this noisy signal, conditional on that being the true value. You can hopefully trust me that this is the correct specification. Take the derivative again, and it turns out to be 0. In other words, the bidders are exactly indifferent to deviating up to any higher bid that's in the support of equilibrium bids. Okay. So the bottom line is that in this equilibrium, there are lots of binding upward constraints. In fact, all of the upward incentive constraints are binding. Okay? And my claim is that this is the information structure and equilibrium that minimizes revenue. I'm not going to give you the complete proof, but I'm going to give you a partial proof. I'm going to prove to you that this equilibrium minimizes revenue within a restricted class of information structures and equilibria. Okay? So you notice that the no information equilibrium, the complete information equilibrium, and the one that I constructed all have the feature that the winning bid is a deterministic function of the true value. Right? In no information, it was always a half. It's a deterministic function. In the complete information case, it was always the true value. And in my construction, it was 1/3 of the value. Okay? So in all three cases, it's a deterministic, and in the last two, strictly increasing function of the value. So I want to think about equilibria of that form, in which the winning bid ends up being deterministic, strictly increasing actually, and also symmetric. I want the equilibrium to be symmetric so that both bidders are equally likely to win at any given winning bid. Okay. Now, in any equilibrium, bidders have to not want to deviate from their equilibrium strategies, and the question is, what restriction does that place on this beta function? Right? Beta is sufficient for calculating revenue in the auction, and I want to see what constraints come from the equilibrium conditions. I want to look at a class of deviations of a very particular form. And we call these uniform upward deviations. And basically what these say is there's a uniform upward deviation for every bid. And the deviation says whenever in equilibrium you would have bid less than this level, deviate up to that level. If you were going to bid higher, keep bidding what you were going to bid. But if you were going to bid less, deviate up. Okay? And of course, this is a feasible deviation for the players. And so in equilibrium, they can't want to uniformly deviate up. And actually, you can formulate the uniform upward deviation constraint just in terms of this beta function. Okay, if you deviate up in this manner, there are two things that are going to happen. One is, whenever you were going to win in equilibrium, you're still going to win because you've deviated up, but now you're going to pay more, right? So in particular, whenever you were going to get a winning bid between beta of 0 and beta of v, you're still going to win, but you're going to pay beta of v instead of beta of x. And in ex-ante terms, that happens with probability of half because it's a symmetric equilibrium. On the other hand, you might gain from winning when you would have lost. When are you going to win? Well, you'll win whenever the other guy was going to win, with probability of half, at a bid beta x with x less than v. And in that case, you'll get the true value of the good, which is x, because the other guy bids as a deterministic function of the true value when he's winning, minus this bid that you've deviated up to. Okay? You can rearrange this inequality to conclude that beta of v has to be greater than this expression. Now, we want to minimize revenue. Revenue is just going to be the expectation of this beta function. So on the whole, decreasing beta is going to lower revenue. So an intermediate question is, what is the smallest beta could be, subject to the restriction that it be non-negative, and that it satisfy this inequality? And it's not too hard to conclude, actually, that the optimum for that problem has to solve this inequality as an equality everywhere, at least in the support. Okay? And the reason is that, on the whole, lowering beta lowers revenue. So if this constraint were slack, it would mean you can lower beta of v without giving anyone an incentive to uniformly deviate up to that point. But actually, lowering beta lowers the right-hand side as well. So it further relaxes the constraint, meaning that this perturbation is feasible. Okay? And you can verify that the solution with beta of 0 equals 0 and satisfying this constraint with an equality gives you beta of v equals v over 3. So in other words, the equilibrium that we constructed solves a relaxation of the original problem where we just optimize over this winning bid function subject to these uniform upward deviation constraints. Okay. And in fact, you don't need to assume symmetry, and you don't need to assume this deterministic winning bid. Even if the winning bid is allowed to be asymmetric and stochastic conditional on the true value of the good, it has to be the case that any equilibrium winning bid distribution has to first order stochastically dominate the winning bid distribution in the example, which was uniform between 0 and a third. Okay, so 1/6 is a global lower bound on revenue and equilibrium in this setting. So there are a bunch of methodological connections of this work. I haven't attempted to give an exhaustive list by any means, but the stuff that I think is most closely related within economics is the stuff that I have worked on with co-authors and co-authors on robust predictions in games of incomplete information. But obviously there's also a deep connection to AGT and algorithmic mechanism design. And it strikes me that there is a connection to the smoothness arguments that we've been talking about, in the sense that the smoothness arguments are about looking at a particular class of deviations, like say deviating from whatever your equilibrium bid is to bidding half your value, and then adding up a bunch of those incentive constraints in order to derive a relationship between welfare outcomes that we're interested in equilibrium. And we're kind of doing something similar. We're looking at the incentive constraints where you deviate from equilibrium up to some higher bid, and we're adding up those constraints across all bids that you make in equilibrium to get this uniform upward constraint. And then the larger objects that tells us about is the cumulative distribution of winning bids. It gives us a restriction on the cumulative distribution of winning bids. Okay? So, I think people who work on smoothness have done an amazing job in the sense of generalizing those arguments beyond one particular mechanism and saying, if I have smoothness parameters for any given mechanism, then I can apply similar methodology to obtain bounds. we've only done this for the first price auction, and I don't know to what extent a similar methodology might generate predictions about revenue for other mechanisms, but it's an obvious direction to go for future research. Okay. So that was the example. Going beyond the example, this argument generalizes to basically any distribution of a common value. It doesn't have to be uniform. It generalizes to any number of bidders. It generalizes to any arbitrarily correlated distribution of values where the bidders have idiosyncratic values that could differ from one another. Okay. For some of the results, we do need to assume symmetry of the value distribution. If it's an asymmetric distribution, these methods give a bound, and in the case of symmetry, the bound is tight. So I want to spend a couple of minutes talking about how the approach generalizes to that broader class of models. So we can write P for the measure over values. And there are some, we basically make some smoothness assumption on P. That's kind of a technical restriction, but it nests the common value case and independent values cases. So you should think of it as kind of a weak condition.
I'll ask later.
Okay. And we kind of know what happens with mass points, but the math gets messier. So for a clean exposition, this seems like the right way to go. So similar to the example, we first find a bound on revenue, a lower bound, by looking at a relaxed program. And then we construct an equilibrium that attains the bound to prove that it's the true minimum. So the relaxed program involves minimizing expected revenue, not over all of the equilibrium objects, but just over the marginal distributions of winning bids given the true values. Okay? And that's what this object is, this H. This is the CDF of I's winning bids given the true profile of values, except that it's not actually a CDF because it's multiplied by the probability that this guy is going to win when these are the values. So if you sum this across all bidders I, then you'll get the cumulative distribution of the winning bid given the profile of values, regardless of who makes that winning bid. And we only impose a subset of the incentive constraints, which are these uniform upward incentive constraints. And you can show that those constraints can be formulated just in terms of these cumulative distributions of winning bids. And again, there's a component which is the loss from paying more than you would have if you followed the equilibrium strategy, and a component which is a potential gain from winning when you would have lost in equilibrium. And I say potential because, of course, you might end up winning on some events where your bid is higher than your value, so you're actually losing surplus there. But you might be winning enough when your value is above your bid that you actually do gain from that second component.
Ben?
Yeah?
So the substance of the relaxation is this third bullet. Is there anything else when you relax it? Is there anything else that you?
Sure. There are some feasibility restrictions on H that they have to be non-negative. They have to sum to less than 1.
Those you continue imposing.
Those we continue imposing.
When you go to the minimizing revenue over just all distributions of winning bids, are you losing anything about the original problem beyond the incentive?
Sure. I mean, I don't know anything about the distribution of losing bids. I haven't retained enough information to evaluate whether or not there's an incentive to point-wise deviate from a particular equilibrium bid up to some higher bid. I can't evaluate those, and I can't say anything about whether or not you'd want to deviate down. So I have lost a lot of information, and just because I have a solution to this relaxed program, that doesn't imply that it automatically extends to an equilibrium. Does that answer your question? Okay. So the characterization is somewhat more involved, and in the example it involves several steps. Before, symmetry of the equilibrium was an assumption. Now it's a conclusion. Okay? I'm not going to take you through it. Here, in the common value example, efficiency wasn't a concern. Everyone had the same value. It didn't matter who got the good for efficiency purposes. And the good was always allocated just because of the way we constructed the mechanism, or what we assumed about the mechanism. But when the bidders have idiosyncratic components to their valuations, efficiency is a concern. Okay? And it's far from obvious that minimum revenue would be obtained in an efficient equilibrium. And the reason is that introducing some inefficiency destroys surplus. In principle, the seller might suffer from that loss of surplus in the form of lower revenue. Okay? But it turns out that actually minimum revenue has to be obtained in an efficient allocation. And the reason is that when you deviate upwards in this manner, you actually don't care what your value is on the event when you were going to win in equilibrium, because you're still going to win, because you're deviating to something higher. What you care about the most is what your value is when you were going to lose in equilibrium, because now you're going to win on that event and gain additional rents. And on the whole, having lower values when you lose induces a weaker incentive to deviate up. Okay? And what's the allocation of the good that's going to induce the lowest losing values? Well, it's when you make the winner the guy with the highest value. Okay? So the efficient allocation in some sense is aligned with reducing the incentives to deviate up. Another conclusion, and this is kind of subtle, is that at the minimum for this relaxed program, the winning bid is only going to depend on certain statistics of the profile of values. It's not going to depend on all of the values. It turns out it's just going to depend on the average of the n-1 lowest values. So that's what this object is. You're summing up all of the values and then subtracting off the highest and then dividing by n-1. So why the average of the lowest values? That seems kind of arbitrary. Well, basically it comes from the assumptions of symmetry. Okay, if you uniformly deviate up to some level b, all you know is that you're going to start winning when the winning bid is b, when you would have lost in equilibrium. Okay? But you can't control which of the profiles you're going to win on, which of the profiles of values you're going to win on that you would have lost on in equilibrium. And in particular, if there's a profile of values in which you would have lost and now you're going to win, you're also going to win on all permutations of that profile of valuations. So in expectation, you basically think that your value on this event is going to be the average of your value across all permutations. And combining that with the fact that you would have lost in equilibrium, you know that you expect your value to be the average of the values you would have had in the event that you lost. Okay. And then the final pillar of the characterization, at this point, we know that the allocation is going to be, we know that the equilibrium is going to be symmetric, the allocation is going to be efficient, winning bids are going to depend on the average of the losing values. And then the last piece is what is going to be the correlation structure between winning bids and this average losing value. And it turns out that the right structure is to have the winning bid be strictly increasing in the average losing value. Okay, so these objects are going to be comonotonic at the minimum. And the reason is that, for each one of these uniform upward deviations, the incentive to deviate in that manner depends on your expectation of your value in the event that you would lose, which is, in a sense, the expectation of the average of the losing values when the winning bid is below this level. So the incentive to deviate up is weaker if that expectation is lower. And there's a particular correlation structure that minimizes pointwise for each uniform upward deviation what the expectation is of this average losing value, which is to make the two comonotonic. If you didn't get that, don't worry about it, but the long and short of it is that there's a final form for this relaxed program, which is choosing a deterministic and strictly increasing function of the average losing value for the winning bid. And this kind of puts us back into the situation where we were in the toy model, where we were just optimizing over that one function. And we can use the same techniques as before to conclude that all of these upward incentive constraints are going to bind, and that pins down what this function is. So the general form for the solution turns out to look like this. Q is this distribution of the average losing value. So this is something that we derive from the prior over values. F is going to be Q raised to the power n-1 over n. And then the winning bid, the minimum winning bid function, is going to be essentially the expectation of a random variable, which is distributed according to this F, conditional on it being below the true value of M. Okay. I don't have a great intuition for exactly why this is the form that the minimum winning bid function has to have, but this is what it has to have. Okay. So because this was a relaxation of the original problem, we can conclude that revenue in any equilibrium has to be at least the expectation of this minimum winning bid function. And then the main theorem of the paper is that there exists an equilibrium in which the winning bid is this deterministic function. I don't want to get on the internet right now. There exists an equilibrium in which in which we exactly obtain this lower bound on revenue, and this equilibrium is efficient, right? And therefore, this equilibrium is also maximizing bidder surplus. Basically, we've maximized the total size of the pie. We've minimized in absolute terms the amount of that pie that the seller is going to get. So we must have also maximized the amount of the pie that the bidders are going to get. Okay, so that's the main result. And you know, I suppose there is a lot to do in the construction of the rest of the equilibrium that attains the bounds and in showing that all of the other constraints are going to be satisfied in equilibrium. It's kind of it's an interesting process, but an involved process, and so I'm not going to go into it right now, but yes?
Could you repeat what you mean by the symmetry of the winning bid? The equilibrium is not necessarily symmetric.
Well, what I meant in particular is that the solution of this relaxed program has to be symmetric. And what symmetry means here is I have a winning bid distribution which depends on the profile of values. If I permute the players' identities, this object should remain the same. So in other words, if I swap I and j, now this should be equal to, you know, what j's winning bid distribution was. Or if I swap the values of other players other than I, this object shouldn't change. That's what I mean by symmetry. Yes?
So, not that I saw all the details of your paper as you guessed, but from what you're showing, it seems like the kind of constraints you're using would be correlated equilibrium, will be also the kind of thing one gets in correlated equilibrium as a constraint.
Absolutely.
And the question, is what you're concluding applies to correlated equilibrium also?
Absolutely. So this is a game of incomplete information, so we have to be more specific about what we mean by correlated equilibrium. There is a particular notion of correlated equilibrium, which is something that was invented by Dirk and Steven, that they call Bayes correlated equilibrium. And basically, we're calculating minimum revenue overall Bayes correlated equilibrium, but that is equivalent to the exercise of minimizing revenue overall information structures and Bayes-Nash equilibria. That is a general characterization. So for the purposes of this...
I need to connect this better, but the reason I'm asking, because some of these correlated equilibria are learnable in a repeated setting. If the players do some sort of no-regret learning, that they're going to get to a correlated equilibrium, and the advantage of that is that they don't have to know what the other players know because learning doesn't need so much information.
True. So there are people here who I would like to talk to about this. I don't know to what extent people have extended those learning results to incomplete information environments. But if one did, then I suppose this would be a prediction also about the outcome of that kind of a learning process.
Although those algorithms converge to a correlated equilibrium, you don't know which one typically. So
Correct, but if he's giving a lower bound on all correlated equilibrium,
that
then
would
I
also
think
that
I'm
one,
in
I
game.
guess. I see.
There's also we call it equilibrium in the strategic form, which I don't think are the base, whatever, call it equilibria that you're talking about.
It should be a subset, I would think, of correlated equilibria of the normal form of the game, right?
I think it applies. I mean, one thing what we're doing with Jason and Vasily, we're talking about coarse correlated equilibrium, and what he needs is correlated equilibrium, because the upwards deviation is not a uniform deviation, it's just uniform upwards. But I think that won't be a problem.
Of course, it's also a deviation in the strategic normal form of the game, right? It's definitely something worth thinking about more. Okay, so I only have a couple of minutes left. We call the model that I've been talking about so far the unknown values model. Unknown values in the sense that the bidders might not know anything about their value except for the prior. They have to know the prior. Now, in many models of first price auctions or other auction mechanisms, we assume a lot more, right? So in particular, you know, this might be a sensible starting point in a common value model where learning about my value is equivalent to learning about others' values. So there's a very strong strategic linkage through what you learn about your own value. But when you talk about models with an idiosyncratic component, like, for example, the independent private values model, it's often reasonable to assume that the bidders are more informed about their own idiosyncratic component than about others. And an extreme version of that is what we call the known values model, in which you definitely know your own value, although you may have partial information about others' values and what others know. So basically, we study the known values model as well. And we conduct similar exercises of trying to derive bounds on revenue and bidder surplus across all information structures that satisfy this condition. And there's kind of a natural restriction here, which we impose, which is that the bidders don't bid more than their known value. Okay? If you knew that you were going to lose for sure in equilibrium, you might have an incentive, it might be incentive compatible to do that, but it's a weakly dominated strategy, so it's kind of a natural refinement. So basically, we characterize maximum revenue for the known values model. The long and short of it is that in the unknown values model, in a symmetric setting, revenue could go all the way down up to the efficient surplus, and bidder surplus could go all the way down to 0. That's no longer the case with known values. In general, the bidders can guarantee themselves some positive rents, and we compute exactly what the maximum rents are that the bidders can guarantee for themselves and minimum revenue. Sorry, we calculate the minimum rents that the bidders have to receive, and we calculate maximum revenue. Okay? We also explore minimum revenue in the known value setting, and we attempt to generalize the techniques that work so well for unknown values. It turns out that they don't generalize completely, but we can solve some special cases. For example, when the bidders have two possible valuations, high or low. In that case, we can completely solve the model with n bidders and get a tight prediction for minimum revenue. Although more generally, of course, unknown values is a superset of known values. So our unknown values minimum revenue characterization is also a lower bound on revenue for the known values model. So this is a gratuitous picture, as Larry Samuelson would say, of the set of welfare outcomes, combinations of revenue and bidder surplus that can obtain under these two models. The blue outline encircles the set of outcomes that could arise under unknown values, and then the red set is known values. And this is for the case of two bidders who have independent, uniformly distributed values. So basically in this model, this is the efficient frontier in which the sum of bidder surplus and revenue is maximized. There are inefficient equilibria in which the sum of those two objects is below the efficient frontier. Okay? And these are what the whole set looks like. This isn't an analytic characterization. This is obtained computationally. Although we have analytic characterizations for various features, this frontier, this point, and this point, and some stuff along here.
And the talk has been about what part of this picture?
The talk has been about minimizing revenue in the unknown values model and maximizing bidder surplus in the unknown values model. This one was trivial, because this is when the seller gets everything and the bidders get nothing. In the common value model. It's not trivial in the general model. And then I briefly mentioned results about this point. Okay. So let me wrap up. There are a bunch of applications that one could imagine for this work, and we do some of them. We think about what would be the effect of introducing some kind of exclusion device, either a reserve price or an entry fee into the auction. We know that in the classical setting of independent private values, that can raise revenue. And it seems like it can also raise revenue here, although it's really just a computational exercise that we do. Another application is, there's a large literature in economics on auction econometrics. We observe some distribution of bids, and we want to back out the fundamentals of the model that gave rise to those bids as an equilibrium phenomenon. But that literature typically makes strong assumptions, like, for example, IPV or affiliated private values. So the question is, there are some obvious applications of this result to identification. I have a distribution of winning bids, and I know that whatever the true environment is, the minimum distribution has to be lower than what I observed in the sense of first-order stochastic dominance. And that imposes a restriction on what the true distribution of values could be. And then, as I was briefly mentioning, we look at some other directions in welfare space. How low could efficiency go? I suppose there is a nice connection that I should mention, which is that there are results that I believe Eva has worked on, and Vasilis Sirganis, on lower bounds on efficiency in known values models. that apply to this general setting, actually. And it's kind of a remarkable feature of this computation that known values minimum surplus is so much higher than unknown values minimum surplus. In fact, for this independent values setting and symmetric setting, you can show that surplus could go all the way down to completely, always misallocating the good. In other words, there is an information structure and an equilibrium in which the winner is always the bidder with the lowest value. I'm not going to construct it for you now, but it'll be good coffee conversation in a few minutes, hopefully. But in the known values case, that can't happen, and minimum surplus is significantly higher. Okay, so I'll wrap up. In future work, we're hoping to extend this methodology to understand other mechanisms, and then the super long-term goal would be thinking about mechanism design from the perspective of max-min, where I don't know what the equilibrium will be, and I don't know what the information structure is. So, thanks. I answered all of your questions preemptively. Thanks.